to limit gravity, but just in case, like thank you, and I wish we can make I can meet all of you in person at some point. So today I'm gonna be speaking about some recent work about like how to try to describe gravitational waves like during the spiral phase, like of emerging and compact binaries using amplitudes. So that's a quick plan of the talk. If there is some urgent question, also please interrupt. Like it might be better to clarify sometimes. So I will start talking about the post-Minkowskian expansion. So how we define perturbation theory using particle physics approach like to general relativity, and how we can find classical scattering amplitudes we contribute to the gravitational interaction of point particles. And this is kind of the leader under description, like somehow at large distances, like of the gravitational interaction of two compact bodies. Then I will move on to describe a framework for bound states, and in particular based on the Bethe-Salpeter equation, how to take the classical limit, how to make the connection more clear between scattering and bound states. And at the end, like I will show split the relation from scattering and bound observables, in particular talking about the waveform. Okay. So I think that we are in a special point, like now in time, like that with the discovery of gravitational waves. It's really like an exciting time, like for studying, like with two analytical techniques, the two-body problem. And in particular, what we need are waveform templates. The reason is that if you want to extract the signal for a gravitational wave, which you see here, you will have like the different gravitational waves emitted like a different stage of the evolution of these compact binaries that can be like black holes or neutron stars. And especially for the spiral part, this is where we can use like point particle effective field theory tools. But we also have techniques to deal with the mergers. So far, they're only numerical, but maybe there is some way of approaching it in an analytic way. And the ring down instead, like we can use black hole perturbation theory. What we try to do is try to put together analytical and numerical techniques to span the whole parameter space of the evolution of these binaries, and combine it with some big frameworks like the effective one body or the self-force approach to try to get the full waveform over the entire evolution of the binary. For today, I'll just focus on the spiral phase, which is the regime in which you can use effective field theory to study the evolution of the compact binaries. And this has been pointed out, for example, in a very nice paper by Goldberg and Rothstein, 2004. The whole idea is to model these compact objects as point particles, the interaction, and add higher order effects as some kind of higher order dimensional operators, which will be suppressed. So this is a kind of summary table of the idea of from real world to effective field theory of point particles. So if you have a compact object of mass m, we will model it with a point particle of mass m. If we have some spin effects, so curved black holes or spinning neutron stars, like this will be some spinning particles of classical spin A. We can have tidal effects or jerk curvature corrections, and both of them can be described as some kind of higher dimensional operators. And these actually mix up with each other as well. And then we can have absorption effects. So what I will describe today doesn't have absorption. It's a unitary process like in particle physics, but in general, you can include also absorption. I will focus today on the case of the point particle of mass m, and in case I will also add maybe some spin at some point. But it is important to remember that you can add higher order effects in a systematic way, and the framework allows you to do that. Okay. So one question can be why amplitudes? So there are a lot of people doing general relativity for already bound orbits. And so you have to ask yourself, like, why it's important why this is a good approach for that. So the amplitudes are gauge invariant objects that encode the perturbatives, the perturbative dynamics of point particles. The interesting part is that they are universal and analytic. And especially the fact that they are analytic, like it's something very useful, like in general, like because of when you want to describe like a signal and you want some analytic templates, clearly the more you can push the analytic understanding in the of the signal, like the more you get closer to the dynamics. And when there are too many cycles, as there will be for LISA, for example, the new space interferometer, which will be launched like in 10 years or so, like it will be impossible, like only with numerical techniques to approach the case of many orbits. The error will accumulate. So the fact that you have something analytic is very important. Another point is that they give a new perspective on GR. So when I first studied GR, like you learn about Schwarzschild black hole. Essentially, you study spherical symmetric metric. You impose your symmetries with the Killing vectors, and that's how you find like the Schwarzschild solution. But here, like you can study the Schwarzschild metric, for example, by studying the coupling of point particle, matter point particle, like with Gravitational. And that will reconstruct the metric for you. So in some sense, like it's giving a new perspective on GR. And I think there's still a lot to learn about this. And finally, I mean, these methods are adapted to scattering orbits. But as I will say something at the end, like we can also discuss bound orbits, like through some analytic continuation. So these are the reasons why I want to take this approach. And as I already mentioned, in 10 years, we will have this, the LISA mission will be launched. And basically, I think for extreme mass ratio spiral, especially, like the fact that you have so many cycles makes analytical techniques even better. I mean, that's the point where you can really push like more analytical understanding and give something really useful, maybe to astrophysicists. Okay. So I now go to the theoretical part, theoretical description, like of the interaction of this point particle. So the idea is to take two particle states, okay, P1 and P2, and you smear with some wave packets, psi1 and psi2, that are separated by some input parameter. The idea is that we want this to evolve like a classical. So we are talking about the scattering case, okay, right now. We'll talk about later about the bound case. And this wave function are localized on the classical trajectory, as we'll discuss more in detail later. And the idea is that you take your Einstein-Hilbert action, so it's the standard Ricci term, and then here I just choose a minimal coupling. Remember that I can add higher dimension operators, other things, okay? Spin. Here is just a scalar coupled to gravity, minimally coupled to gravity. And the idea of this particle physics amplitude approach is to expand the metric, this G mu nu, as the flat metric plus the gravitational perturbation, H mu nu. And so this derives to some Feynman rules. And this kappa like is related to the Newton constant. This gives rise to the post-Newtonian expansion in the Newton constant. So basically, you do a power counting, okay, of your diagrams based on this coupling once you expand this action, and this will give rise to the Feynman rules at the bottom. Of course, I mean, nowadays we don't use Feynman rules with better techniques most of the times, but they're still useful to remember like where they come from. Okay, so this is the state, this is the dynamics, so this is how the state will evolve. Okay, and now I will describe more in detail how to take the classical limit of this. So in particular, also how to describe classical observables. So classical observable, you compute them like in quantum mechanics. Quantum mechanics, you take expectation values like in expectation values, so you evolve your state with S metrics. And you take your in expectation value, so you have the S matrix and the conjugate. When you expand the S matrix as a disconnected part plus the trivial connected amplitude, you will get contribution linear in the amplitudes and quadratic ones. So these are really related. If you've heard about Swinger-Keldysh formalism, it's exactly the same thing. And we're taking some classical on-shell reduction of that. So on-shell because we're taking the on-shell limit of these external states, and classical because the wave packets that are in psi will localize on the classical limit. So, but is essentially really the plus-minus basis in the Swinger-Kelly. So we're just using, as I said, expectation values of quantum mechanics, like for quantum field theory. Okay. And in particular, also one thing I want to mention, there's both contribution, both linear in the amplitudes and also quadratic here, the C case, which are these Cutts terms in general. Okay, so now how do we take the classical limit for the scattering of point particles? So for the massive particles, so we want to excite that I was describing before, we want some minimum uncertainty wave function localized on the classical trajectory. So in particular, you take a wave function of this type, some exponential. This P is the momentum of external particle, okay? So these are the 4 particle scattering. So you have the 2 massive particle coming on the left and leaving at the right, okay? And you see these wave packets, these little wiggles, like you want them to localize in a trajectory, okay? Just like when you do trajectory with geodesics or the world line approach, it's exactly the same idea. So the momenta of the particle dotted into the 4 velocity, it is the classical 4 velocity, is weighted by a factor, this h bar LC. LC is the Compton wavelength, and the LW is the spread of the wavelength, is weighted at this factor such that when you go to h bar to 0, essentially this factor is very high, and it will localize in a kind of WKB sense, okay? Your quantum scattering into a classical scattering. In the rest frame, you can just think about this as a Gaussian in this case. And of course, we want to impose some hierarchy of length. So this is effective field theory, okay? So as I was saying, like you want to model your particles like in a special regime where they are far separated, okay? So in particular, your input parameter distance between them must be larger than the spread of the wave packets with just this kind of finite distance effects. And of course, everything must be larger than the Compton wavelength. So Compton wavelength is a quantum effect. So it should not appear in the calculation. And so essentially, you see it's exactly proportional to h bar. So you need to expand that. That has to be the smallest parameter in the game. So this is the kind of hierarchy of scales we want to impose for this program. For massless particles, we can use coherent states. I'll just mention later a bit about that, but it's not really important. Okay, so this is for the states. Okay, now we want also the classical limit for the amplitude. Okay, so this is a kind of so the idea is that every massless particle must that is a change as a massless momenta, okay? And this massless momenta just has to scale like h bar. The reason is like think about Planck quantization, okay? So you have E equal h bar nu with the frequency, like, and you take h bar to 0, you reduce to the classical spectrum. It's exactly the same, repeated for all the massless particle in the game. So in particular, here the massless exchange on the right here is the graviton in this 3-level 4-point amplitude, and so you need Q to scale like h bar. And if you restore everything, like in terms of the kinematic invariance TNS, you see this is exactly equivalent to Regge limit or Iconal limit. So there are various names. In this example in particular, they are all equivalent. So you see T must scale like h bar squared, so T over S is very small. And that's exactly the Iconal limit as it's called. So it's a regime that was well studied before even talking about this limit, but I just want to, the reason why it's the same is because the parameters scale in the same way. And if you want, like, it's just an expansion in the momentum transfer, okay? So now for the 4 plus m point amplitude, like you do the same. So instead of having only the exchange, the virtual exchange of the graviton, you will have also external graviton emitted. So they also have to scale like h bar. So there is no secret. That's the same idea. And the main lesson when we take the classical limit is that only wave vectors are classical. Okay, and we need to restore h bar. And in particular, I want to mention also that also loop amplitude can contribute to the classical limit, because this imposing this scaling is not exactly equivalent to taking only the saddle point. I mean, to say cosine the saddle point level of the action, you need to do this further expansion in Q So only also loop level amplitude will contribute in general. Okay. Any questions on this before I move to waveforms? Okay. So now I want to, just like before I was mentioning, we want to take expectation value of operators, just like in quantum mechanics. And we do that for the gravity operator. So what we obtain, we do that is exactly the waveform. So you take h mu nu, sorry, is it something? Okay. So if you take h mu nu, bracket into the states, then when you expand the h mu nu in on-shell modes, you get A and A dagger. Okay, it's the standard quantum filter expansion. You will act on a state which has two massive particles that will create a graviton. So it's no surprise that when you create that graviton, what you end up with, the leading order is something like the 5-point amplitude, which is here. Okay, so here 1A, 3A are one of the two massive particle. The other pair is 2B for B, and then the 5 is the graviton. You will have like your polarization vectors. And then essentially there is this object, which is the integral. So of course you don't have only the amplitude, there is an integral, phase space integral. Okay, just look like normal observables like cross sections. And it's weighted by this wave function, which will eventually localize. So the structure is not really important because for me, actually should be relevant to be more precise. And one interesting thing is that this is essentially, as we'll discuss soon, like you can think about this as a kind of stress tensor. So it's a kind of stress tensor of the binary, okay? This J tilde contracted with epsilon mu nu is essentially that. So you're integrating over that, as I will discuss soon. And okay, we work now only leading post-Minkowskian order. So it's only expansion leading order in G for this observable, which will mean the index is proportional to G squared. Okay. Okay, so one thing I want to mention that is very important is that in classical physics, you only have retarded boundary condition. Okay, you solve the classical equation of motion, the boundary conditions are retarded. So if you look at my expression before, like you see there is 2 times real part and there is an exponential. So this is combining the amplitude and the conjugate amplitude, okay? So it's combining the I epsilon and minus I epsilon pieces of the amplitude. And you will have this exponential, and then because it's a real part, you will have exponential of plus, right? So when you take, what you want to do when you consider waveform, the waveform will be the leading 1 over R component of h mu nu, which is the only on-shell one. So here, we are not really reconstructing the metric because we are using the on-shell expansion. So only radiative degrees of freedom will be computed by this one. You need so if you want to get something like the metric, it will be to have, it will need to be off-shell, okay? So here it's on-shell, I've used the on-shell mode expansion. Okay, so anyway, if you take some measurement distance, so the R direction, okay, we're far away from the object, much far away to the input parameter, so there is yet another kind of hierarchy of scales. There is a unique and well-defined direction. You can essentially take this larger limit and combine it to exponential and get the retarded propagator. So these are retarded physics just come into play, okay, from because the waveform must be function of retarded boundary condition at the end. So the expression that we got is of this form. So now it's simplified. So I already removed the wave packets. And essentially, I contracted also the h mu nu with epsilon mu nu just to define a scalar, okay? So what you see here is that you will have like this J tilde, and these J tilde are exactly, as I said, like essentially a stress tensor for the binary, okay? The advantage of a stress tensor for the binary is that here it's a non-shell formulation of that, okay? And in particular, these J tilde are integral over the momentum transfer of the 5-point amplitude, which function the 2 transverse momenta. So Q1 and Q2 here are the difference between P1 minus P1 prime and P2 minus P2 prime. So they exchange momenta by the 2 pair of massive particles, okay, in case the momentum of the graviton. And you need to do, okay, this Fourier integral and then a final Fourier transform to get from the frequency domain waveform to the time domain waveform. And you see also the retarded time appears here when you do this procedure, which is exactly what should happen because the waveform will be a function, explicit function at retarded time. We're now ready to start to compute scattering waveforms. I just want to mention that we can use on-shell tools at this point. This is quite technical, maybe with respect to the rest of the talk, but what you can do is basically you see this measure d mu. You want to use the property of the S matrix. So we know that three-level amplitudes are rational with poles. So there's the specific analytic structure. Remember, analyticity is important here. And so what you can do, you can try to compute these integrals by essentially exploiting the analyticity properties like in the complex plane of the amplitude, and in particular factorization channels. So the 5.3 amplitude is simple factorization channels with only poles. So you can try with some suitable coordinates to localize this integration, okay, with complex analysis tools. I won't discuss too much in detail, like we wrote it in this last work recently. But basically, what you gain from this is that you can get very compact representation for the three-level waveform, okay, which is only a function essentially of 3-point and 4-point amplitude without any integration. So you can localize completely all the integration, and that holds for basically any theory where you can do this factorization. And so this, even if you see here, there's a lot of integration in red layer, this one can all be localized. So at least at tree level, okay? At tree level, when you have poles, and one loop, you will have discontinuities. You will have to be more careful, go around the branch cuts. But at least at tree level, like this can all be localized, and it gives very complex expression. These are Kovacs and Thorne original result in the 80s. And there it was written in a few pages. Now it's just 4 lines, okay? So you get very compact result. This is one of the main achievements, I guess, of the amplitude community, like in many directions, like that you always get like very compact results, gauge invariant compact results. And this is one of those, I think. Yeah, so of course, it matches the old result and also some other recent work by the Merlin group. Okay, so this for spinless. We also did the spin case, but I'm not going to talk about that. But I just want to show that you can get something very, very compact, okay? The variables here are not important. There are some retarded time, T1 and T2, and some dot products of the momenta, essentially. Okay.
Can I ask a very quick question?
Yeah.
Yeah, so like, is there a contribution from the contour at infinity, the SW that you've written in all of this, or you only get contributions from the poles?
So there is a contribution at infinity, which is related to the very good question, to the soft theorem in this case. The thing is that we have used a symmetrized prescription. So we close the contour in the upper half plane, and we do 1/2 the contour in the upper half plane minus 1/2 the contour in the lower half plane. And if you do that prescription, then you will remove the contribution at infinity.
Oh, okay. Thank you.
But if you just close a 1/2 for the contour, like, you will get that contribution. Anyway, it's easy to compute.
So
it's
that contribution would be the Weinberg factor, is it?
Yeah, 1/2. Yeah,
okay.
1/2 the Weinberg.
Okay,
Yeah.
thank you.
Thanks for the question. Yeah, indeed, like as in
May I ask
many
another
other.
question?
Yeah.
Well, my question is also like one. Well, what's the information do you need to know in advance to perform this computation? So, for example, do you need to know the trajectories of the 2 particles?
No, yeah, indeed, this is an advantage here. So everything I've done is all gauge invariant. So trajectory is a gauge-dependent choice, and here we don't need to do a trajectory. So we just need to do this 5-point amplitude, which is built on the Feynman rules I described earlier. So this is working in momentum space fully, okay? So we don't.
Okay,
Yeah.
so once you specify the initial condition of the two particles, then that's it.
Exactly. That's it, because it's just like in quantum mechanics that you evolve your state with S matrix. So you just say if this S matrix was your interaction Hamiltonian, you would evolve with that. And then essentially you would just take expectation value at the end, right? So it's exactly doing that in perturbation theory, essentially.
Oh, okay. Thank you very much.
No, you're welcome. Yeah, thanks for the question. Right. Other questions on this before I move on? Okay. So if you plot it on the equatorial plane, this waveform, you find something like this. So the equatorial plane, the imaginary part actually is 0. And the real part looks like this. It's like a step function. The reason is that this three-level scattering, most of the energy is released during the periastron, so the closest approach. Okay, so that's scattering. So when the bodies are close enough, that's where most of the energy will be released. Okay, so this is a scatter event where I start with scattering, end up with scattering. So there will be a unique situation, a unique point in time where these bodies are close to each other. That's not what we want. We want the bound case, but I'll discuss later out from this one, we can go to the bound case. Okay. And I just want to mention it's very different from the quasi-periodic bound waveform I was described at the beginning. So, and there is the open question is, is it possible to establish a connection? Okay. Okay. So now I'll try to go to this and try to understand how bound states can be tackled in this picture. So class scattering amplitudes describe what is called hyperbolic encounters in GR. And essentially, what it means is that if you construct the binding energy is the total energy minus the sum of the masses, okay? So it's positive for scattering and negative for bound. A better variable is also this one, P infinity. It's related to center of mass momentum with infinity for scattering. So you see, this is the square is positive for bound, and then the square is negative for the square is positive for scattering, and it's negative for bound. And in particular, so the P tilde infinity is actually imaginary. So sorry, the map is imaginary from P infinity to P tilde infinity. It will be important later. So the idea is that we have some hyperbolic motion. Okay, this is scattering on the left, and that will become some sort of ellipse. Okay, and the idea is we bring the energy, we lower the energy in our expressions. The expressions are analytic, so we can do this, and we try to connect with something bound, like where the energy is below the threshold, essentially. So there are two powerful methods to extract bound state physics. So one of them is extraperturbatively the classical potential, the Hamiltonian. So these are interaction, right? So two-body interaction. So if you go to center of mass frame, you do Fourier transfer, you get something like a potential. And this you can do. And this has been important. This works. But something that I think also very interesting is that there is a gauge invariant map between scattering and bound observables. And in particular, this map can also be derived from the Bitter-Sabiter equation and can be extended also to waveforms, which is what I'm going to discuss today. And the idea is that you have an observable, which is a function of the binding energy and momentum, tidal effects, spin and masses, and you can somehow connect it to something related to the bound observables with an analytic continuation in the sense of complex analysis in some. But okay, as you will see, like there are some factors. Relative factors in between. Okay, so I will start with something very, very simple because I think I want to bring everyone on the same page. So how can we step bound state of point particles? Just start with Coulomb solution, okay? So Coulomb solution is if for gravity becomes linearized Schwarzschild background. So you take the Schwarzschild background and you span linear order in M, okay? You span time metric. You put you use the Hamiltonian of that system, so there were one potential over here, and you solve the Hamiltonian. So here it's like Coulomb, so Coulomb is solvable problem, okay? So you can map this differential equation for the wave function into a solvable Coulomb potential. So here you want to study scattering and bound solution for this simple example, just to show that we can solve this so we can exactly understand how transition from scattering to bound happens at the very simplest level. The difference with Coulomb is that the factor here is the energy dependent, essentially, on the 1/r potential, but that's the only difference. So now it's a familiar eigenvalue problem, like in quantum mechanics. You have like your free term, and then your interaction term proportional 1/r, and linear in the coupling. So you see the coupling is here, so it's here. And you can solve it with different boundary conditions. So you can take scattering boundary condition, as I was discussing before. So you have a scattering plane wave, something that looks like a plane wave, an infinite past and future, and that will give rise to a continuous spectrum, okay, when you solve this eigenvalue problem. Or you can take some normalizable wave function, something that decays at large distances, and that will give rise to some discrete spectrum. And this is solvable because, as I said, it's mapping into Coulomb, so you can solve it. So I want to now discuss the solution of this, which are kind of well known, but not the relation in the classical limit and the exact details of this. So what is the relation between scattering and bound wave functions? So for scattering wave functions, what you get is a confluent hypergeometric function, okay, which is a very well-known solution. It is this the 1f1 over here, okay? And it has also an interesting pole, which I'll discuss later. And notice here, the scattering is very important. The scattering is a sum of partial waves. So when you study bound problems, okay, you put some quantum numbers in your solution that are labeling the solution. And the bound solution here is directly the one with the quantum numbers. So for example, it's already proportional to YLM to the spherical harmonics, okay, in the partial wave basis, whereas the scattering one will be a sum of partial waves. So what you have to do is to transform the scattering solution, the familiar confluent, in the partial wave basis, which is a key part. And then once you go to partial wave basis, there is an interesting relation that we found. And this y variable is essentially to the p infinity I was discussing before. So 1 minus y square is actually, square root is actually p tilde infinity I was discussing before. And you notice two things. So first, you take the scattering solution, you do the analytical continuation with a single branch prescription, okay? The fact that there is a plus and not a minus here is actually dictated by the fact that you need to map this exponential over here, this plane wave, to something damping that comes from the Laguerre polynomial here expanded, okay? So there is a sign, I think this is related to causality and boundary conditions. And then you have to take a residue. So the interesting part, there is also a residue to be taken. And this residue is because like you need to essentially extract the residue of this gamma function. They are not exactly this because you have to go partial wave basis. So there will be a gamma function with shifted values, but essentially this is what is happening. And this, of course, is a prototype of the type of relation we want. So we have like wave function for scattering and bound. So now we can extract observables for scattering and bound. But you see there is a residue here that really is not really convenient. And also, as I will discuss soon, like it's kind of redundant. It's related to the iterations, as I will discuss soon, as we'll see. Okay, so here y is E over m. Okay, so it's positive above 1 for scattering and below 1 for bound. Remember, we are in the probe limit. So there is a useful formulation in terms of P infinity and PTL infinity, which are variables that I'm going to use again, which is this one. And the thing to notice, the residue comes from the bound state pole of the amplitude. This wave function, of course, I mean, it's the amplitude essentially, okay? When you expand the wave function at infinity, you remember the prefactor of the outgoing wave is essentially the amplitude divided by the ingoing wave. So yeah, can we simplify the map? So what is this residue in particular? And here, here is where like a perturbation theory actually tells you something interesting. So here we solve everything non-perturbatively, okay? So it's an unperturbative solution because we just take the linearized Schwarzschild and we just compute the eigenfunctions. So that's an exact solution for that linearized Schwarzschild, which is also equivalent to three-level PM in the two-body. So what you can do, you can think about the potential, the 1 over r g over 1 over r, g over r potential, okay? And you do the iteration. And you see, so this is the potential I'm considering here, okay, 1 over r. So you can solve this by perturbation theory. So I solve this exactly, I can solve this by perturbation theory. So I can take expectation values like the potential and do the iteration like Born approximation. And you see that basically only the potential itself, when you do perturbation theory, should be relevant when you study things in perturbation theory. Okay, I hope later will be clear the connection why I'm now discussing perturbation theory in this way. But essentially, if now the linearized force field background is generated by another source, in the non-relativistic limit, you essentially get this ladder approximation, which is the standard non-relativistic approach. The standard non-relativistic contribution to a 2D problem at 3 level. And this can be written as some kind of amplitude recursion relation, okay? One thing, so one of the points that the bound energy pole, the one that we have taken the residue, is generated by the iteration. So if you don't iterate, you don't generate a pole. So there is a hope that maybe, you know, the fact that you're taking the residue is just because you iterate things. You just need the single term. Of course, we need to confirm this. So if you write this recursion in amplitude as a amplitude recursion relation, you find essentially the two-body like the Swinger-Dyson equation in the own after LZ reduction. So the amplitude, this is the amplitude recursion relation for the 4 points, is essentially exactly equivalent to Swinger-Dyson equations. For the two-body with respect to two massive particle, okay, reducible diagrams. And this kernel K, which is this my 3-level amplitude here, is what essentially used for the iteration. So in perturbation theory, use this kernel. So at 3-level, the Km doesn't contribute, so you get like that M4 is equal to a 3-level term, and then you just keep iterating, okay, in the ladder. So the ladder is generated by this iteration. Okay, so we just recast perturbation theory in a kind of different language, but we haven't solved anything yet. So,
so excuse me,
yeah.
may I ask another question? So relevant
Oh,
to
sure,
this.
yeah.
So you say that here, okay, so when you consider the bound orbit, you have the discretized energy levels.
Yeah.
Right. Then are those equivalent to the perhaps quasi-normal modes, or maybe not?
No, because quasi-normal modes are different boundary condition. So, but for quasi-normal modes,
okay.
The differential equation has to be solved with the absorption boundary condition at the horizon. Here, there is no horizon.
Okay, then, but nevertheless, you still have the discretized energy levels. Then what kind of boundary condition do you impose? So maybe at the far region, you might impose one boundary condition, and perhaps you have to impose another boundary conditions, which makes the energy levels discretized. Is that right?
So we are not really I impose boundary condition for the solution of these wave functions, which are just that it's normalizable. So you need like the inner product to be finite. And that as a consequence will give rise to this result. But in general, for the amplitude, you imposed boundary condition in the past when you do the scattering. You do the scattering and then you can continue the result. So I impose just boundary condition for the scattering for what I'm going to discuss.
Okay, then going back to the previous slides, you showed the previous okay. So I think you showed Schrödinger type equation. Then to solve this, well, what kind of boundary condition do you impose? At far region, maybe if there's no injection, purely outgoing at infinity, right?
So these are incoming plane wave in the past. which then you then evolve, and then you find some outgoing plane wave in the future. Essentially, it's a Klein-Gordon inner norm for the wave function, whereas this one has normalizable inner product for the wave function. And then essentially it gives you some decaying property of the wave function. I don't know if that helps.
Okay, thank you very much.
Yeah, we can come back to that later, maybe, in case.
Ricardo, can I ask a question? So in some sense, you also need to determine the spectrum by direct solving the bound state problem, right?
This is only for this example. I just want to show the relation. I will do it differently later. Yeah.
Also, can you incorporate radiation in this case later?
Oh, yeah. That's what we have done. Yeah.
Thank you.
Yeah, I'll come to that later.
Ricardo, so just to confirm, so this kernel K is not necessary, just the 1 over R, you can include higher orders? Is that correct?
Yeah. I'm just talking about the fact that you need only the exponential, the exponent in the exponential at the end. I'm just trying to build that up, essentially.
Good, thanks.
Yeah, you're welcome. Thanks for the question. Okay, so this is the equation. So just giving you recursion relation for 4-point amplitudes. Okay, it is non-perturbative in a sense. And the idea is that bound state energy poles arise from iteration of 2 MPI kernels. So that are the one like the 3 level that I was describing. So you have this kind of equation, is a self-consistent equation. So you have K on both sides. You see it's iterated. And you can solve in perturbation theory, usually for the quantum case. You have also the two-body propagator. You see this one here in the iteration, and there is a convolution involved. So usually this is where things kind of stop, because here, I mean, this is it's an integral equation. That's really highly non-trivial. But in a classical limit, like there are some simplification, and one of the reasons why this should happen, if you think about geodesic solution, right? Everyone can solve geodesic non-Schwarzschild. So essentially, this should arise from this kind of formalism. So there is a way. I mean, there must be a way to make this calculation like streamline, like essentially also in the classical setup, and that's indeed what will happen. So the classical limit of this is a quantum equation. Involves essentially symmetrizing over internal graviton exchanges. So what you can do essentially, this is a bit technical, but essentially here, this iteration of the kernel with a 4-point amplitude, you're exchanging some gravitons between the two massive particle lines, and you don't want to distinguish any graviton in the classical limit, because otherwise it's a quantum process to distinguish a graviton. So you symmetrize over that, and once you do the symmetrization, essentially you combine the massive, in the classical limit, you combine like the different pieces with the massive particle line emitting 2 gravitons and the cross version, and essentially it will give rise to some cut propagator. This is like very similar to terms that appear in the word line approach, where there's always this kind of linearized delta function of energy conservation. So what happens is that the two-body propagator in this recursion gets replaced by the on-shell version. And it's not really important. I just want to, make the contact now with why we don't need to take the residue, essentially. But I'm going to come to that soon. So what happens is that the 4-point amplitude can be written as some iteration. This for when you have the kernel, but now you don't have. So the two massive propagators, the two massive part propagator is cut, and the convolution here. So you get 2 delta function that you can solve 2 integrals, and then you are left over. You see Q minus L. You are left over with a convolution, and the convolution in the direct space is a product in the Fourier conjugate space. So what happens now? We need to go to hyperparameter space. The interesting thing is the hyperparameter space is exactly partial wave basis. So again, I'm now generalizing partial wave basis for a wave function to essentially the classical limit for open amplitude. Okay. The reason why it doesn't look like partial wave basis, but it's exactly doing partial wave basis. You're fully transform this Q momenta, this Q change with the hyperparameter B. And once you do that, then this Basel-Peter equation, this classical Peter equation, just diagonalize essentially, and you get you can solve. You can see from here. So the m+1. So this m grading is the number of two massive particle reducible diagrams. Okay, and it's just a technicality, but essentially, what you get is that only the K kernel is generating this three-level term, okay? It's relevant for the solution. And in this input parameter basis, then a solution exponentiates. So you get exponential of the kernel -1. And this is exactly like WKB type, okay, solution. So remember WKB, you have e to the I over h bar as your classical action, is exactly that for the 4-point amplitude. You need to go to this input parameter space. Also, the reason why it's partially based is that this B is related to the angular momentum, okay? So as we'll see. Okay, I'll go quickly because there's not much time. Yeah, so the analytic structure in momentum space is also quite interesting. From the point of bootstrap, the amplitude completely arises from the inverse Fourier transform integration. So if you give me the kernel, if I can compute this Fourier transform, I can get all the poles. So the poles I was describing before, remember the gamma function pole in the scattering, just arise from the integral of the kernel, and the kernel will be very simple. So it's exactly a three-level term. So what I'm showing here is that if I focus on the kernel, I can do a better analytic. I can do a better analytic continuation like that than considering the amplitude, because I don't need to take the residue essentially. Okay, so I'll just give an example before going to the radiation. I'll be quick because I'm running out of time, but essentially the classical kernel up to 2 p.m., so second order, this G expansion is just given by 3-level and 1-loop triangle diagrams, and is of this form, okay? So this is exactly a diagram we're considering for conservative dynamics of two spinless particles. So B is now, sorry, it is expert, okay? And the interesting part about this is that the motion is restricted to a plane. The reason you can see this is that you can map all these quantities, these dynamical quantities, to energy and angular momentum, and also this rapidity y. Sorry, and the rapidity y is also related to the energy and the masses. So essentially, everything is determined by energy and a single angular momentum. So, and this is the reason why you know the dynamics of a two-body problem. You can always, for conservative case, you can restrict to a plane. This is exactly what we are finding, just written in different variables. And this is, if you want, the potential up to 2 p.m. So G squared, essentially. G squared is here. Okay, so since we know that we have scattering dynamics for E greater than 0 and bound orbits for E less than 0, how do we perform analytic continuation? So now we have a function of E. So remember this Y function of E and the binding energy. So we can try to think about how to do analytic continuation. Naively, you say, oh, just do analytic continuation on this. This turns out to be correct, and as I'll now describe, you need some combination of terms. So this kernel is essentially the Hamilton-Jacobi action. I mean, in particular, the radial action, okay? And you can just notice by inspection, this has been noticed by inspection, essentially. So you have an integral over dr of your radial momenta, and then you have also a factor L pi over here. And this makes a connection between the amplitude, the 4-point amplitude, and the exponent. Remember, we are using the exponent now, exponential of k. It gives us the connection with classical dynamics. So classical dynamics is, standard Hamilton-Jacobi type of actions, just arise from the integration of this, just arise from this kernel. So if you compute this kernel, the two massive particles diagrams, you will get, in this conservative case, the radial action. Okay, so this radial action is now a function. Okay, you have the radial momentum in the integrand, and then in the contour of integration, you have to integrate for scattering from the minimum distance of the hyperbola, okay, to the infinity. That's the scattering for this dependence on the radial part. For bound, you will have integral between the turning point of the ellipse. It's just standard Hamilton-Jacobi type of analysis. So if you do that and you look at the analytic properties of the turning points, you'll discover that there is a relation that we found like between the turning points in terms of these p tilde variables and the L, the one for scattering. So there is only one turning point for scattering. So scattering, you know, go to the scattering, you have one turning point, then you bounce back. But the same turning point, if you just do one analytic continuation or the analytic continuation, you recover the two turning points of the ellipse. This is highly non-trivial. It turns out to be the case. And because of this, now you can rewrite, you see the contour of integration of scattering. You have two integral Rm to infinity. You split it up. You know that PR depends only on the square of infinity, and you can find the relation of the following form. Basically, this relation is telling you that the bound radial action is related to the sum of scattering radial action with different analytic continuation of this p tilde variable. Okay. Okay. We can easily compute observables with this. So both for scattering angle, it's just derivative over L, and periastral advance is derivative. Is also derivative of F, but it bounds radial action. So once you have this representation, everything is kind of straightforward, at least for a conservative case. I won't have time to discuss, but actually it is generalized to aligned spin particles because they stay on the equatorial plane. And we also recently discussed the case of generic Kerr orbits like processing. But today we want to talk about radiation. So very quickly, that the previous picture of the iteration. Okay, so this two-body recursion relation for the amplitude, or four-point recursion relation for the amplitude. What you can do, you can just add a graviton emission, okay, a positive graviton emission, and dress all your recursion relation. So if you dress the previous recursion relation that I was showing here, this one, okay, you add a graviton everywhere, okay. Essentially, you recover the Swinger-Dyson equation where you actually emit a graviton, so for the 455 points, and you will find a recursion relation for the 5-point amplitude, which is what is relevant for the waveform. Okay, so now we are, remember, for the 4-point, we have a relation between the wave functions, okay, which comes with a residue. That residue is not relevant anymore because we look at the kernel, and now we want to find a kernel in the 5-point case, so we case with radiation. If you apply the symmetrization procedure, you will find some similar iteration in the previous way, where the previous case that where the two-body propagator gets replaced by the on-shell version. Okay, and so here everything is a function of this relative kernel. Okay, and this is still given by two massive particle reducible diagrams where you attach your graviton. Okay, so can a solution exist for this resummation? So this is the interesting part. So here again, you can use the Fourier transform of convolution idea, okay, which is a mathematical statement about Fourier transform of convolutions, to find a very simple structure for the S matrix, which, as I said, is generalization of WKB in the case with radiation now. So you don't have anymore only the 4-point kernel. So now you have two input parameter because there are two exchange momenta. As two Q1, Q2, so each of them has his own input parameter, if you want. Then the result will be dependent on the difference, but in principle, you will have two different length scale associated to the momentum transfers, and then you will have an exponential of the relative kernel. So the naive structure is that your S matrix and all orders for classical limit like will be essentially exponential of your 4-point kernel and some coherent state exponential of the 5-point kernel. So why I'm showing this? Because we understand the analytic continuation of the 4-point, right? That's what I just described, okay, in terms of the radial action. So what is now the 5-point? So now we're gonna go to the radiation part. And of course, all the observable scattering and bound can be derived in a gauge invariant way from the two kernel. Okay. And one open problem, yeah, we want to solve, can we understand analytic continuation of the wave? Can I get 10 more minutes after 9 since I got some questions?
Yeah, no problem.
Okay, thank you. Okay, so if you follow the linearized Forshell case, okay, we got the wave function for scattering and bounds, remember? there was a residue, and there was the partial weight basis thing. So the partial weight basis is taken care by doing the Fourier transform in parameter space. That's what I'm saying. That's we're going to partial weight basis. The residue is taken care by the exponentiation. So if you combine these two statements, you find that naively you would expect that your waveform, I say here dynamical. I'm not talking about static effects today. So I'm talking about positive energy, right? The gravitons. I can talk about memory separately if you want. So the bound waveform is related to the scattering waveform by analytic continuation with a single branch cap restriction for this P infinity. Okay, that's the same as the Schwarzschild case, just now extended like to radiation, like and taking into account these two steps of residue and partial weight basis. Okay, how can this be verified? So why we should trust this expression? Because I mean, in principle, we just it's a conjecture. So we can use post-Newtonian expansion. So we can use the waveform central mass frame to make contact with a multiple expansion in time domain. For example, done by these authors. And in particular, okay, people usually doing frequency domain expansion in PN. Here we do in time domain, so we need to do a rescaling of the retarded time. It's just a technicality to get to the 1/c expansion. So post-Newtonian expansion is expansion in 1/c. Okay, so and essential expansion is low velocity. So V/c is suppressed. So that's why this U was related to U. It comes with e to the omega u in the with the frequency. So if the frequency has to be small, you need to rescale the retarded time to take into account that to get the correct post-Newtonian expansion. That's why I'm rescaling the retarded time here. Okay. So the interesting part is that PN multiples can be independently computed for bound and unbound using quasi-Keplerian parameterization for hyperbolic and elliptic orbits. This was shown a long time ago by Tamor and Derwell. And so we want to recompute this expansion, the expansion of the waveform like in PN. This coefficient can be recomputed independently in bound and unbound, so we can check the map that we're now proposing. So that's the one on the top. Okay, so here there are other equations, but it's not really important. I mean, the multiples are a function of relative trajectory, and the relative trajectory involves like, essentially the quasi-Keplerian parameterization involves really the parameterization of the ellipse and the hyperbola for the relative trajectory. So the ellipse will be this this function over here, where essentially you have dependence of trigonometric function. Okay, for the radial, this is the radial distance in this relative trajectory. So it's a difference between the position of the two bodies. So now I'm making contact with trajectories since I got the questions later. Now I'm making contact with trajectories, but I'm just checking things that they agree. For the hyperbola, now you have instead like hyperbolic functions, so hyperbolic cosine. And what you find is that if you parameterize the orbit in this way, so it's really a geometric parameterization. The orbit is gauge dependent, so that's gauge dependent. But you can find that up to 1 PN, so here there are 1 PN corrections, you can map orbital elements into each other. It's just, and you can do that by just analytically continuing the binding energy. So the fact that I was proposing before, you remember the fact that it's only analytic continuation binding energy, and this waveform is a function of the multiples, and the multiples, as I now discussed, are a function of trajectory, makes perfect sense. So the fact that only the energy is relevant for the analytic continuation at the end. Okay, to make contact with really post-Minkowski expansion, you need to expand the large centricity. So what happens here, there is never a function explicit of time in post-Newtonian. There is always an implicit function through an anomaly, and that anomaly satisfies then an equation related to the Kepler equation, just a standard Kepler equation. So the time is an implicit function of this, and because this is a transcendental equation, you cannot solve it analytically. You can solve in terms of infinite sum of Bessel function if you want, but it's transcendental, so there is no closed form solution. What happens is that if you do the post-Minkowskian expansion, the expansion in coupling is an expansion in eccentricity, you can solve it a large centricity, this Kepler equation. And so what happens is that you can find your trajectory r cos of theta, sin of theta in terms of time, which is what you need, because you need to make contact the waveform in terms of time, which I need to check with my post-Minkowski result. Okay, so long story short, you compute the quadruple, so it's just a standard quadruple formula, GR. you compute it with this relative trajectory. Now you function time explicitly. And this matches the PM 3-level waveform expansion. So we could get an agreement. This is for scattering still. But we also check for bound. And at the end, what we find is that there is a boundary to bound map between relative multiples for hyperbolic and elliptic orbits up to 1 PN. So the interesting thing is that there is an interesting paper which was computing like 1 PN wafers. This Juncker and Schaeffer like a long time ago, in bound and unbound. But they never mentioned that there was an analytic continuation, but we just checked. And essentially, even if you don't expand in post-Minkowskian, you can find analytic continuation between multiples up to 1 PN. Beyond that, there are tail effects, and it's a bit more complicated. We can come back later in the questions. And so this gives an independent verification of our map. Okay, so because now we can claim that there is analytic continuation on the multiples, and this translates to analytic continuation on the waveform in time domain. So I'm talking about time domain is quite. I also mentioned this. So you remember I was talking about on-shell tools to compute time domain waveform. This residue and complex analysis theorem. So the waveform in time domain, the analytic structure is much simpler than the waveform in frequency domain. And indeed, we were able to find a localization of the waveform in terms of 3 and 4 point amplitude only in time domain. In frequency domain, there is still an integral to do. So you can translate analyticity properties of amplitudes into waveforms very easily in time domain, but not so easily in frequency domain. Anyway, okay, that's just an aside comment just to make this clear. Yeah, so using the new map for the waveform, we compute the bound waveform, for example, at 3-level with the split expression was shown earlier, and we recover the PM multiples computed with the elliptic trajectory. So we got, and at 3-level, you don't have problems, so you recover the full 3-level bound waveform. So now, how is this? So, we can plot it, is it nice or not? So this is what happens if you naively do that. So you just analytic continuation on the left, that was the previous result I showed. And now you get this one on the right, which is the new result. So you see basically the real part turns into the imaginary part, and you get nothing more. So you say, okay, that doesn't look like a bound waveform. The thing is that there is something subtle about expanding large centricity and the fact that and because it's expansion in the coupling, and you need to resum, you need to perform a resummation. If you do it naively, the bound waveform is not periodic in time. The reason for this is very simple. So essentially, the type of sine function, for example, that appear in the full waveform, they're function of some angle which is expanded in PM. So it's like if you had a Taylor series of the sine, okay? So sine of u equal u minus u cube, whatever. So it's a Taylor series. So you don't recover all the terms in the span. You need to resum to get something trigonometric oscillating. So that's what we are about to do. So if you now perform the resummation in the eccentricity, so what it means is that I don't truncate the solution of the Kepler equation that I was before. So before I have a Kepler equation, remember I truncate as an expansion in large J in such a way that essentially the equation is not transcendental anymore, because if expansion large J at the leading order, then the oscillating term is gone essentially. So if I solve it completely, I do recover what I want. So this is a numerical solution. Sorry, it's a numerical solution on the Kepler equation, not the waveform. But so if you find the relation between T and V, then you see the scattering waveform look like in the right, and then the bound waveform finally is oscillating on the right. So basically now there is. You see that's what you want. So basically, you see the right branch of the scattering waveform now becomes this oscillating pattern that is what you want, like in the bound case. Remember, we are still talking about spiral phase, and we're still doing essentially 3-level Newtonian essentially physics. But I just want to point out that because you need to resum the PM expansion. This is not new. It has been done also for the conservative sector, but we are here extending for the radiative sector. And in this case, finally recover something periodic in time. It's just the starting point of this. Okay, yeah, you need to read some perturbative contribution. I'm not talking about that. I think I'm almost done. So I'll give a quick summary of analytic continuation observables, although some of them I haven't touched. So the scattering angle, just like the radial action, remember radial action, you take derivative over L. So if there was a relation to the radial action, you can find a relation to the scattering angles per astron directly. They can all be written in terms of analytic continuation of the energy. So some of the previous analytic continuation were in terms of angular momentum flipped is not needed. You can just use the branch cuts of your amplitude in terms of, of your observables in terms of the binding energy. So that's all you need for all the observables that we know so far. And the new result is that we have this analytic continuation of the waveform, which is in agreement with the prescription of the orbital elements. Okay, so I'll close it here. Okay, there is tail effects to be studied, so I'm happy to discuss that in the later with the questions.
May I ask a question?
Um,
Oh, sorry. Okay. Sorry. Thank you for the your nice talk. So, I have a question about the okay. So the validity of the analytic continuation of P infinity. I think here, I think the P infinity is implicitly assumes that it's constant. But in realistic case, the radiation may lead to the kind of back reaction onto the trajectories, and the P infinity or the angular momentum of the particles is not a constant values anymore in that case. Then even in such a case, can we still validate the analytic continuation? Or what do you think?
Riccardo, are you still there? I don't think we can hear you.
Can you hear me?
We have your second last slide. Oh, sorry. I think.
It's sorry. Do you hear me now?
Yeah, we can hear you now, and it was stuck on the second last slide. It was on the summary slide 30.
Oh yeah, it's all I'm done anyway. So yeah, thanks.
Okay, so you don't need to share the slides. Okay.
Oh, it's stop shared or
Yeah.
Okay.
So you covered the 3 bullet points on slide 32.
Yeah. It's just frozen at the moment, my Zoom, so I don't know. Just a moment.
It's not a problem. I guess if you'd like to stop here, we can stop here and have either a verbal an audio clap, or we can put the clap sign.
Okay. Yeah. No, that's fine. I can hear you, so I mean you can talk. Yeah. So anyway, it was just summarizing the last slide, so there's nothing more than that. Sorry for that. Sorry about that.
Okay. Did you hear Oshita-san's question?
Happy to take any questions.
Oshita-san was asking a question.
I can ask a question again. So okay, so and yeah, thank you for your nice talk. So I actually asked a question about the validity of the analytic continuation of P infinity. So I think during the talk, it was implicitly assumed that the P infinity is constant, but in realistic case, taking into account the back reactions of the radiation onto the trajectories, the P infinity or L, the angular momentum of the particles is no longer constant, right? Then even in such a case, I think if you are aiming to apply the technique to construct the model of the waveform for Lisa or something like that, you need to care that point. And in that case, still, can we validate the analytic continuation of P infinity, which is no longer constant?
So let me say one thing. So the P infinity in this the scattering scenario is fixed in a sense that is your incoming energy minus the two masses normalized by the masses. So in the scattering sense, it is well defined from the outset. Of course, then you analytically continue for the bound, but it's just the two-body energy of the system. But it's the incoming one. So but the boundary is about the boundary condition we're asking. So indeed, like it's fixed by the incoming boundary condition. For the angular momentum also, this angular momentum I'm talking about is the one in some sense again of the two-body system, which is well defined for the scattering setup when you impose the initial state. So what we can get here indeed is the analytic continuation of that scenario, provided, of course, there is this problem of non-local in time effects, which I haven't addressed yet, so that will appear higher orders. Also, yeah, it's what I want to say. Yeah, for the they will appear also the radiation reaction we're mentioning on the two-body system. It will be taken into account by this. Okay, so the fact that the multiples, for example, are defined with respect to a different center of mass frame will be taken into account. Is an higher order effect. You can do the power counting in this framework, and it's an higher order effect, but it will be taken into account. We don't use really the trajectory, so I use the trajectory only for checking the results, but I haven't used for the actual calculation with the amplitude. The amplitude is self-consistent, and as I said, you can include different type of effects, higher orders. But the P infinity and L are fixed in my case because of the two body that you evolve with your S matrix.
Okay, so in this form, in this program, you can naturally extend to the situation where you need to take into account the back reaction of the radiation.
It's already built in the system. It's already built in. So I do expect if you check the relation with the multiples, so it has been checked up to one loop in the waveform at the moment, and it completely agrees. So if you can take into account the radiation reaction, the next order, it will be relevant. So you need to compute the multiples to come back to the back reacted center of mass frame, but then it will match the new result that I get on the true loop of waveform or whatever, whoever will get it. Let's say like that.
Okay. I see. Oh, that sounds, very powerful. Okay, thank you very much. Thank you.
Yeah, no, it's all gauge invariant. That's a nice part about this, what I'm saying. It's all gauge invariant, so that's one of the advantage, like that you don't need to restrict to a frame. You can restrict a frame for checking things, but not, it's more general.
Fixing the gauge is very trouble in the GR context. So, but that's a very good news. To me. Okay. Great. Thank you very much.
Well, we're still starting with this, so this is all very new. So I mean, it's it's still much more to do. Shashank, you have a question?
Hey, thanks for a nice talk, and thanks for getting us so early. So the very last part wasn't entirely clear to me. So I just want to understand when you say you compare between the hyperbolic waveform and also the bound state elliptic waveform. So do you mean that you compare this at level of these multiple moments?
I compare the multiple moments, yeah.
And
directly.
So the multiple moments evaluated for the hyperbolic orbit versus the elliptic orbit, and then compare using this analytic.
So yeah, the quasi-Keplerian parameterization is valid for anything, right? So for bound and unbound, there is an explicit expressions up to 3pn order for bound and unbound. So you can take that. You solve the Kepler equation perturbatively in exponentially large eccentricity. You plug back into a trajectory. At this point, trajectory time dependent. It's something that you
Yes.
usually cannot do because of the side transcendental equation. But if you linearize with the perturbative expansion, you can do it. And then you compute the multiples as time dependent, and you compare that with the expansion of the waveform in PN, and that agrees.
So my question is that so in this expansion, does that mean that for the elliptic orbit, it's also around this like very large actually? Yeah, how should I E very close to 1 in the so what's the orbit for the elliptic?
Good. So I mean, you need to do analytic continuation going to the imaginary plane for the eccentricity. It's a bit non-trivial. It's implicit in the resummation.
Oh yeah, so it's imaginary, yes.
You need to perform some analytic continuation, like, because the eccentricity is very large,
right?
And you want to get back to something, and so you need to. So when you solve Kepler equation for the bound, usually you still need to solve it a large J essentially. You still need to solve it a large centricity. So that will give you something that is unphysical for the bound, but then you analytically continue back, and it gives the right answer. I don't know if that makes sense. So you can compute with the parameterization of the bound orbits. You can compute the multiples expanding a large eccentricity, and that would be unphysical. But that will make contact with actually analytical. I mean, you can then bring it back to the physics.
What do you mean unphysical for the elliptic, for the bound case? What do you mean by unphysical?
So it will, I think, I mean, it's not real below 1. That's what I'm saying. I think it's actually imaginary, if I remember correctly. When you solve the Kepler equation. You need to at the end the result will be valid for eccentricity below 1. You just need to do analytic continuation outside the domain of validity when you compute bound multiples in PM. But there's maybe a way to bypass this.
And okay, I need to think about what you said, but and also when you said from like the naive one, when you go to the periodic, so can you explain again how you get the periodic waveform?
Sure. I can try to reshare apologies for the problem when Zoom was frozen. I don't know what. Oh, it's still okay. No, my connection is okay. Maybe it's better if I don't reshare. I don't want to get frozen.
It's
but
okay. Yeah.
I'll explain to you. That thing. So done is I didn't solve the Kepler equation perturbatively in G, okay, or in large eccentricity or in large J. I solved that numerically to get T in terms of the centric anomaly, and then I plug back in the full. So you can compute So you can compute all the time domain multiples as PM people. So you never as a function of time. So the waveform in PN are a waveform in terms of the anomaly plus a Kepler equation. So there are 2 lines: Kepler equation and the waveform in terms of the orbital elements. And then I solve numerically the Kepler equation, I plug back in, and I do get agreement both with. So I get the periodicity. So essentially, I'm resumming the solution of the Kepler equation effectively. We haven't shown how to implement that directly at the level of the waveform, but that's what is happening. Okay. So you want to reconstruct. It's like reconstructing a sine function from the Taylor series. So you need. So there are some methods. We have not yet exploited all the power of this. Like I think there's still some room. I mean, some room for. But essentially, that's what we are doing. We are trying to reconstruct the sine function from a Taylor series in a more.
I see. I think if I understand you correctly, you sort of take the multiple moment like perturbatively, but for the trajectory, you actually solve that non-perturbatively in not using this large J expansion. You plug in the fold.
Exactly.
And then once you plug in, then you get the periodic waveform. I see. Okay.
But you can always still expand. I mean, if you expand, you recover what we have in PM. If you don't expand, you get this resummation.
Right.
So what you want to do is getting, as I said, essentially getting some methods for this is, I mean, very similar to what people have been done already in other contests. I mean, even for the conservative case, there is this fears of resummation, other type of techniques, where there is an unperturbative information, some way of resumming some extra contribution. This has to be done for the waveform too. That's what I'm getting at.
It makes sense. You can always declare that you only want to do strict perturbation theory in some quantity and then stop on there, do other things non-perturbatively. So
it's not ideal, but this is what has to be done to get something that looks like something oscillating. It's the bound case that makes sense. So I think anyway, it is still very investigation. So
sounds good.
Thanks. Other questions?
Yeah, I could ask one, but like I'll see if there are any other questions. Yeah, I guess I'll get to the question you wanted us to ask about the non-local in time and local in time issues. So like so when you're solving the transcendental equation, are you suggesting that these non-local in time pieces show up at higher orders in this expansion that you're talking about, this Taylor series expansion, or does it show up at some other way in what you're
So in what I've discussed, it doesn't. So up to 1 PN in the post-Newtonian and up to at least 3 level and maybe 1 loop in the PM. It has to yet to be seen. Like these no local in time effects do not appear. So independently of the resummation I discussed on the Kepler, so it's independent of that. So the resummation on the Kepler you can just do for Newtonian waveforms, okay? And that Newtonian waveforms doesn't have any problems with these no local in time effects. Let me also say that, first of all, these are only some gravitational effects. So if you do this for electrodynamics, classical electrodynamics, this will, all the procedure will go through at all loop orders, I think, because these effects are just gone. So it's already a result that somehow, if you restrict to some pieces of this in the classical electrodynamics, that should all go through to all loop orders. Now, the no local time effects are dependent on trajectory. And somehow they depend on the history of the motion. And this dependence on the history is quite subtle. So one thing is that I studied analytic continuation on the final waveform, okay, which is the final observables, which is a phase space integral of the S matrix. In the same way as the waveform can be an integral over the, it's a function of the multiples of the trajectory. So you can ask, is it better to do analytic continuation at the level of the S matrix instead of doing the level of the observables? That's also a possibility. In the same way as I mean, if you do it, let me say like that. So you can take the quasi-Keplerian parameterization. That works also for non-local effects. That's what people have been doing. So even the recent papers computing bound things, they took the Hamiltonian and they plug in the quasi-Keplerian parameterization for bound motion, which works for bound. And so there is in that quasi-Keplerian parameterization, there is no problem in doing the analytic continuation bound and bound at the level of the trajectory. The problem is that you cannot do at the final level of the observable at the moment. So probably what one needs to do is somehow to do analytic continuation earlier. So instead of in classical GR, you should do at the level of trajectory. In S matrix, you should do at the level of the S matrix before doing the phase space integration. So you can ask, can you do the analytic continuation level of the S matrix, just like going in a complex kinematic plane, going beyond scattering kinematics, and then trying to extract from there some physics that you can use for also this non-local in time effect. So that's still an open question. That will make a closer connection between trajectories and S matrix, essentially. Of course, cannot be done completely because S matrix is gauge invariant, trajectory is gauge dependent. So you cannot really ask for that, but you can ask that maybe there is some intermediate quantities that maybe analytically continue. When you integrate at the end, it doesn't analytically continue, but if you do it before the last integration, maybe it works. So this is what, yeah.
And a related
but it's still an
Maybe a related question is like, if you have unequal masses and if you're doing like a self-force expansion, does your procedure carry through, or will there be some differences in that procedure? With that, I will stop all questions from my end.
We are studying that case, so I don't know yet. We are studying that case. So for the self-force, the 1SF effect is actually directly the tail piece. So it directly some non-local integral. But somehow you as I said, it's a matter of where you ask the localization, or where you ask the analytic continuation. So it depends on which variable. So if you do it at the level of trajectory, it still works. So there is a piece of the steps in which you lose this, but at the level of trajectory, it always works. That at least the known cases that I know. It's not ideal at the moment, but at least there is a case in which it works. So for the moment, I would say no. So the geodesic case is fine, of course. The 1SF is not fine yet, but I think it might be possible since it's only a function of the trajectory, the geodesic case, yeah. So it should be possible in the same way it is possible to compute Hamiltonian for bound orbits by using particle parametrization. I hope that answered the question. I don't know.
Yeah, I guess I was just curious because of this paper by Ortho and all, which talks about these non-local terms, and they have like a self-force correction in there. But like, I guess okay. I guess anyway, you might be running out of time.
I can't. Yeah.
Okay, so I
need to go.
I guess there's no other time for questions, so we'll just thank Riccardo again. Thank you very much for your time.
Thank you. Thank you very much. Thank you for a nice talk.
Oh, thanks to you. Sorry for all the time issues. Yeah, I hope to see you all of you in person. So yeah, see you. Thanks a lot.
Okay, thank you.
Thank you.